Hello everyone, we're looking at our new unit on transformations. Transformations are something that will move or change a figure. Maybe it changes the size or shape or location of an object. And so we have a variety of different kinds of transformations. Some are called translations, others are dilations or rotations or reflections, and we'll be looking at each of those on each of these days of notes as we go along. So we're starting off with translating. There's a set of vocabulary words we want to take a look at regarding translations and writing a rule. The rule is the algebraic notation for how we communicate how that object is going to move. Alright, so let's fill in some of these blanks, just starting off with what we're focusing on today, which is a translation. Alright, so we're not translating from one language to another, which is what you might normally think of when you hear that word. Here in this case, a translation is a movement. A translation moves or changes a figure in some way to produce a new figure that we're going to call an image. So another name for the original figure is the preimage. So here the prefix is pre. Pre means it comes before. So this is the image that comes before the movement. So the preimage comes before the movement, and the image is the result after the change. So at the original point, we could have points, we could have segments, we could have triangles or other polygons that were moving, but here we're just looking at a specific point. If the original point is called point P, then the new point, after it is moved, is called P prime. So this is how you say it. And the notation is P with that apostrophe symbol. So it looks like P apostrophe, but that's a prime symbol. We say P prime. And that's how we know the difference between the preimage and the image. Once again, here we are talking about a translation. A translation moves every point in a figure the same distance in the same direction. So if you think of an object like a triangle, it's made up of three sides, three segments. Well, each of those segments are made up of lots and lots of connected points, an infinite number of points. So every point is moved the same way, and that means every side is moved. That means the whole triangle is moved in that same way. So same distance in same direction. So we'll start off with an example using the simplest of objects, just points themselves, and then later on we'll get to the notation, and then we'll get to some bigger objects, namely triangles, and maybe some other polygons. So here in example 1, it says, using the graph at the right, answer these following questions. How would you describe the translation from point A to point A prime? So you can see here's point A and point A prime. How did we move this point to get over there? Well, it looks like it's left and up from the original location, but we want to know exactly how far it's moving, so let's do a count. Starting at point A, I'm moving left 1, 2, 3, 4, 5, 6, 7, 8, and then up 1, 2. Alright, so it looks like point A moves left 8 and up 2. So what we are doing with this description is replacing it with what we're going to call the rule, the notation. So when we say write the rule for the translation, there are three parts. First, you start off with an ordered pair. So this is saying, hey, wherever I am starting my location, I'm going to change it in this way. And if I'm moving left 8, that means my value of x is decreasing. It's going down by 8. So we would say x minus 8. If we were moving to the right 8, then it would be an increase in its value, and we would be adding 8 instead of subtracting 8. There's the comma separating the x and the y coordinate. Here we're moving up 2, so that'll be plus 2. That means our y values are increasing by 2. If we were moving down, we would be moving down. Now, because we have a specific name, we have this as point A and this is A prime. We only have one point here. We could call this A and A prime, describing that specific point and how it's moving. But if we have another point called B, well, then I don't want to just assign A and A prime to the rule when we have points B and C that we might be moving as well. So this is a general rule that can describe any number of points that are moving in this way. So let's go on to part B, and we'll be using that same pattern. If you wanted to use the same translation for another point called B, which is located at 2, negative 2, then where would B prime be located? Okay, so let's think about this. Here's my point B. It's located at 2, negative 2. That's this first part of the rule. Then we're going to change it in this way. And the new name is B prime. And we want to know where that is. Well, we want to take the x coordinates and subtract 8. That tells us we're moving left 8. So let's take this x coordinate of 2, we're subtracting 8, and we get negative 6. Take the y coordinate and increase it by 2, add 2. So negative 2 is my y coordinate, add 2, and we get 0. So without actually plotting any points, we know where that point will end up. Let's go ahead and plot these points anyway. So B is located at 2, negative 2. There it is. And we're saying it ends up at negative 6, 0. So from the origin we count negative 1, 2, 3, 4, 5, 6. There it is. Put the point, label that with the B prime. And now if we were to count the distance from B to B prime, we should be counting left 8 and up 2. Let's check our work. So from point B we're counting leftwards 1, 2, 3, 4, 5, 6, 7, 8, and up 2. Yeah, so that turned out just right. So let's take a general point. This could be anything really, x, y. If we have point C that's located at x, y, in other words, we don't have numbers, then where would C prime be located? That's where the rule comes in. It says, well, I don't really know where the x coordinate is, but I can shift it to the left 8 units. I don't really know where the y coordinate is, but I can increase it by 2. That's the rule with a general x and y, as opposed to the rule with a very specific set of values. So in this shaded box below, we're looking at a very general case. We don't have specific numbers. Again, we're just using this notation to communicate how we can move objects around, and then we'll get to some specific values below that in the next set of examples. It says you can describe a translation by the notation, and you'll recognize this looks very similar to what we were just talking about. That is the rule. There's always 3 parts. We have the general coordinate, we have the arrow indicating some change, and then we have the result. In example 1, we had specific numbers that we were moving the object by. Here we're just replacing those with variables. A is just a variable, however far we're moving it. B is just a variable. It could be positive or negative. The idea is we're moving it vertically. So with the value of x being horizontal, meaning the x is on the x-axis and it's a horizontal, then when we're looking at the x plus a, that is also a horizontal movement, meaning it's shifting to the right or shifting to the left. The y-coordinate is describing its vertical placement. Right, how high or how low that point is placed is represented by the y-coordinate, which means then that if we are moving that y-coordinate up or down, it's affecting that vertical placement. So here's an abstract diagram. Here they're numbering them off as object 1 and object 2. You can see here's object 1, and we're highlighting just one particular point on that triangle, and we're shifting it to the right a certain value, A units is we're just labeling it as, and then we're changing its vertical position And the idea is that if it's true for one point, it's true for every point on the triangle. We can take this top right point, shift it to the right A units, and then up B units, and we'll end up in the exact same relative position. So it works for the whole figure. So what we're doing here is we are showing that every single point, not just one or two, but every point on that figure is translated to the right A units, whatever number that might be, and then up B units, whatever number that might be. If it was down, then it would be a negative value of B. Here are some more examples. Example 2, write the rule for translating right 3 and down 4. So here's my rule. Start off with the x comma y, put the arrow symbol down, and now we're going to change that x. We're going to the right 3, so that's increasing in 3, that's plus 3. And then we're going down 4, so our y coordinates are decreasing by 4. Notice we're not calling it point A or point B, simply because this is a rule that would affect every point on the figure, like a triangle. Here in example 3, how would the notation change if you started at figure 2 and moved to figure 1? So we're going back up to this illustration here, saying, okay, what if we started at figure 2 and we went backwards to figure 1? Well, instead of going rightwards, we'd be going leftwards. Instead of going upwards, we'd be going downwards. So we're going left and down. So we would take this pattern and replace the positives with negatives. So there's my x comma y, there's the arrow, and we go x minus a comma y minus b. Here in example 4, they give us this rule. The rule is take each point and change it in this way, x plus 3 and y minus 4. That's what we were just coming up with previously. And let's apply that to a couple of specific points without graphing. So what is the image of point W, which is located at 2 comma 5? Remember, the image, it describes what comes after the movement. How does it change? Where does it end up? So what we do is we start off with our pre-image, 2 comma 5, put down the arrow, and we end up with W prime, and that's what we have to calculate. So the rule says take the x coordinate and increase it by 3. We're essentially shifting it to the right 3. So my x coordinate is 2, adding 3 gives us 5. Take the y coordinate and subtract 4. My y coordinate is 5, subtracting 4 results in 1. In the second part, it says, what is the pre-image of r prime, which is located at negative 1 comma 7. Now this is an important example. You might want to highlight it or give it a star. Just kind of bring your attention back, because this one, if you're not paying close attention, this one can throw you off, because notice the difference in part A, which asks for the image, and part B, which asks for the pre-image. Now the pre-image, you remember, is the original location. What that means is we have to work the rule backwards. This is the final product. R prime is its final location, but where did point R come from? To figure out where it came from, we're finding the pre-image, where it was before the movement, which means we have to turn the order around. Instead of adding 3, we need to subtract 3. Instead of y minus 4, we need to go y plus 4. So this is working the rule backwards to find the pre-image. That's what you have to do if a problem asks for the original point, that pre-image point. Okay, so r prime is located at negative 1 comma 7. There's my arrow, and we're going to figure out where the original point r was located. So let's take that x coordinate and subtract 3. So my x coordinate is negative 1, subtract 3, we get negative 4. Take the y coordinate and add 4. So my y coordinate is 7, add 4, we get 11. You can check your work very easily by taking this point R and then using the original rule, and if you add 3 to x, and subtract 4 from y, then that will tell you where the point ends up, which is the r prime, where we started. Okay, those are the basics. So now that we've got the notation done, a few examples with some points, now we're going to apply that to some figured shapes. And we'll start off with example 5 here, which is working with a quadrilateral. Alright, in the box at the top, these are the basic steps you want to go through when we are graphing our translations. First, we're going to graph the preimage, and don't forget to label the vertices. Second, we're going to use the translation rule. We're going to use the rule. That means we'll do our algebra to calculate the numbers. Use the rule given to find the coordinates of the image. And then lastly, we will graph that image and label the vertices. Be sure to use that prime notation. We want to keep track of which shape is the original and the new shape. We have a quadrilateral called KLMN with vertices located at, and you can see all those values. Find the image of each vertex after the translation, and here's our rule. Take each point, subtract 4 from x, and add 2 to y. Then graph the image using the prime notation. Alright, step 1, graph the preimage. So let's plot these points. K is located at 0, 2. So from the origin, neither right nor left from the 0 part, but the y-coordinate is -2, so down 2. And label that as K. L is located at 4, 3, so from the origin, 1, 2, 3, 4 to the right, 1, 2, 3 up, there's point L. M is at 5, 2, so from the origin, right 1, 2, 3, 4, 5, and up 1, 2. And lastly, point N is 6, -1. So from the origin, 1, 2, 3, 4, 5, 6 to the right, and 1 down. Now when they are telling us that this is quadrilateral KLMN, that's also the order you need to connect the dots. So I'm going from K to L to M to N. That way we don't cross lines. This will create our polygon. So that's step 1. Step 2 then, we're going to use the translation rule given to us to find the coordinates of the image. And here they're kind of setting it up, saying we're going to make this chart. We're going to make a table. The first column of the table is the original values that were given to us of the preimage. Then we put the arrow down, and then we're going to come up with the resulting location. So this is our next column of information, K prime, L prime, M prime, and N prime. And then setting up some parentheses for each of these. We'll do the math in our head here to start us off on that first line. You can see that they are writing down the values. We'll just be thinking it through and writing down the result. So the rule says, take the x-coordinate and subtract 4. So we're thinking in our head 0, subtract 4, and that'll give us a -4. Take the y-coordinate and add 2. So this is what we're thinking in our head. The y-coordinate is -2, add 2, and we end up with a 0. Alright, so I'm just going to work down the column for the x's and then the y. So take each x-coordinate and subtract 4. So at L, we have an x-coordinate of 4, subtract 4, we get 0. At point M, we have an x-coordinate of 5, subtract 4, we get 1. At N, we have an x-coordinate of 6, subtract 4, we get 2. Now work down the column for the y-coordinates. Each y-coordinate is increased by 2. So for point L, we have a y-coordinate of 3, add 2, we get 5. Point M, we have a y-coordinate of 2, add 2, we get 4. N is a y-coordinate of -1, add 2, we get +1. That's our image. Now if it helps, you can use a second color to plot these, just to keep the two images separate on the graph. It's not necessary. It will help a lot more when we get to our reflections, because sometimes the figures overlap each other. It's kind of your call on what you want to do. Either way, we absolutely must label the vertices with that prime notation. So this point is K prime. L prime is at 0, 5. M prime is at 1, 4. And lastly, N prime is 2, 1. Alright, connecting these dots. So take a look at these two shapes, and I want to ask you this question. Are they the same size? Yeah, they look to be the same size. Are they the same shape? Yeah, they look to be the same shape. Okay, that's good. That's what we want. And that's example 6. Look at the preimage and the image. How do their shape and size compare? The preimage and image have the same size and shape. The preimage and the image have the same size and shape. Now the reason why we're making a point of this is because depending on the type of transformation we do in the days to come, sometimes they don't have the same size and shape, and so we want to keep track of this pattern. When do they stay the same and when do they not stay the same? So we have some vocabulary to attach to this idea, and that's in this next box. A rigid transformation is a transformation that preserves, think of that as keeping the same, its size and shape. There's another word we use. This is also called an isometry. So if you are looking at problems from our book, you'll see the book describing it as an isometry. We are going to call it a rigid transformation because that's a more general way of describing it over a variety of different books and places. And so it's either rigid or non-rigid. So rigid is like it's stuck in its position. Rigid means it's solid. Non-rigid would mean that like it is flexible or it can change. So a rigid transformation preserves or keeps the same size and shape. And that's what we saw in that first example. Alright, so here's a U-try problem. Draw a triangle RST with vertices R, S, and T. Alright, so you can plot that. And then for the image, use this rule. What I want to bring to your attention is we want to set up the table like what we had done in the previous example. So just to kind of get us started together, here's point R at 2, 2. Put the arrow down, and then another column for R prime with some parentheses, and we'll fill that in later. So this is just organizing our work. S is located at 5, 2. There's your arrow, there's the column for S prime, and then lastly point T, which is 3, 5. The arrow, and then there's the T prime. Okay, that's just getting us organized. So turn off the video, see if you can plot the preimage, calculate the new points, plot the image, turn the video back on, and check your answer. Here, let me get my preimage plotted. S is at 5, 2. And T is at 3, 5. Alright, there's my preimage with vertices labeled, R, S, and T. So in my translation rule, I'm going to take my x-coordinates and add them by 1. So we have 2 plus 1 is 3, 5 plus 1 is 6, 3 plus 1 is 4. Take my y-coordinates and subtract 3. So we have 2 minus 3 is negative 1, 2 minus 3 is negative 1, 5 minus 3 is 2. That's what we'll plot. So we have R prime located at 3, negative 1. s prime at 6, comma negative 1, and t at 4, comma 2. Excuse me, that's t prime. And there we go. Take a look at example 7. This is another good one. Take a sort of flag this one too. That's one to keep your eye on as well, because when you're looking at the two figures, you can see we have two triangles. They're the same size and shape, but if we have to write our own rule, it's very important that we take a close look to see which is the preimage and which is the image. Right? So remember, triangle DEF, that does not have the prime symbol, that's the original, that's the preimage. And then triangle D prime, E prime, F prime, because that has the prime symbols, that's the image, meaning that's the change after the movement. So we have to figure out which of the two shapes does not have the prime symbol. So you can look easily enough. You can compare point D with point D prime, or E with E prime, or F with F prime. It doesn't really matter which of those points you use. You just want to pair up a pair of corresponding points. So the D with the D prime, E with E prime, or F with F prime. So let's go with D with D prime. So we can see that we're starting here at point D, and we're trying to move up here to D prime. How would we move from D to D prime? So the point is, you have to be careful that we don't go backwards. We don't go in the wrong direction. We want to go from D to D prime. So let's count the distance from D to D prime. We're going to the right. Looks like a distance of 1, 2, 3, 4, 5. And then we're going up a distance of 1, 2, 3. Okay, so my rule is, do you remember the three parts? First, you need the ordered pair x comma y. Second, you need the arrow. And third, how is x changing? It's increasing by 5, so x plus 5. How is y changing? It's going up 3, so y plus 3. So if you accidentally, on your quiz, only give me this much of the rule, then you're missing a part of it. You're missing a part of the notation, and so you'll get partial credits. You need all three parts. You also need the right numbers, and you need the right signs. Once again, we have this U-try section. This is where we're finishing up with a little bit of a practice. So use this translation and find the results of these three. So turn off the video, try it, and then turn the video on when you're ready to check your answer. Here are the answers, and what you got to watch out for. The tricky one is that part C. That's the one you got to watch out for. We saw an example of this on the first page, but remember, when it's asking for the preimage, you have to work the rule backwards, because we're trying to figure out where this point came from before it moved. That means you would take the rule that's given and change the sign. So instead of x plus 3, it's x minus 3. Instead of y minus 2, it's y plus 2. I want to take that parenthesis out. That wasn't supposed to be there. And so that's the rule we would use to work backwards to find the preimage, and that's how we got the values of -7, 1.